To begin with, we're going to talk about what causes electric current and what motion of particles is responsible for things like light bulbs lighting up. Now, electrical current, as we know, is a measure of the rate of electric charge that moves through a circuit. We talked a little bit about this in our section on electric charge. The electric charge is carried by charged particles, as you might expect. So when these particles move, they represent a movement of charge. We call the moving particles charge carriers because that's what they're doing. They're carrying charge. Any charged particle can act as a charge carrier. If it's free to move and it's charged, then it can carry electric charge. Makes sense, right? Now, when a metal conducts electricity, the electrons in the metal carry the electric current. So, what can we say about the electrons? Well, they're charge carriers. In salty water, we don't have electrons free to move around. Instead, we have dissolved salt ions. Ions is just the term that we use for charged atoms. So the dissolved salt ions, the dissolved salt charged atoms, behave as charge carriers and carry the current. If we have an ionized gas, also known as a plasma, then we have electrons splitting away from the gas atoms. So instead of just gas atoms, we have gas ions and electrons. And because both of these types of particles are charged, both of them can act as charge carriers. So, as we know, we measure current with amperes, or amps for short. In algebra, we represent it with an uppercase I. We know that we can calculate the current flowing through a particular cross-section of a wire using this equation. I, current, equals the change in charge over the change in time. That is, the current through a particular cross-section of a wire is simply the amount of charge that passes through it per second. So, I is the current, delta Q is change in charge, and delta T is the change in time. Now, in a metal wire, which might look something like this, the charge carriers are the electrons. So you can see that in this diagram, all of the electrons are moving through the wire. Now, each electron will have a charge equal to E, that is the elementary charge, minus 1.6 times 10 to the power minus 19 coulombs. Now, when 1 ampere of current flows through the wire, we have 1 coulomb worth of electrons passing through the wire's cross-section every second, right? If we wanted to figure out the number of electrons in that 1 coulomb, we divide 1 by the electron's charge, and we get this ridiculously high number. So when I say the cross-section of the wire, I mean the sort of dotted circle that's been drawn right in the middle, or perhaps the circle at either end. Because charge flows through at a constant rate, no matter where we take the cross-section, we'll always get the same current flowing through the wire. Now let's look at some of the typical currents we might find around us. 1 amp is a large amount of current. We don't usually use laboratory experiments that have a current of more than about 1 or 2 amps. Most currents are measured in milliamps, that is, thousandths of an amp, or even microamps, which are millionths of an amp. Battery-powered devices tend to have very small currents flowing through them. A pocket calculator, for example, has a current of about 5 milliamps flowing through its circuit components. A torch bulb is a bit more powerful. It has a current of 1/5 of an amp, right? 200 milliamps. So 200 thousandths of an amp is the same as 1/5 of an amp. So already we can produce quite a bright light from a torch. We don't really need to get currents larger than this to do useful things with low power. But what if we want high power things? With larger devices, especially ones that radiate a lot of energy, such as lights at a stadium, the currents tend to be much greater in magnitude. The headlights of a car have a current of about 4 amps flowing through them. The electric heater has about 4 amps, but of course most of the energy coming out of it is not light, it's heat instead. House lighting circuits can draw about 13 amps when all of them are on. Now, this gives you an idea of how much current we need to draw to power various devices. How do we measure current? Well, we use a device that might look something like this. It's called an ammeter. An ammeter is a device that measures electric current. They have a very, very small resistance because of how they have to be connected to the resistors that they're measuring the current through. We'll look at more at that later. One common type of ammeter is called a galvanometer. For now, we've finished up the theory for this section. So we've learned about electric current and the sort of numbers that we might expect electric current to get to. Let's go on to some questions, shall we?